Hello everyone. I'm just going to start this week with a video reviewing what we were doing before the holidays. We had been looking at exponential relationships and how to write the equation from the word problem for these exponential relationships. So I've written a few up here and we're just going to look through it again just to remind ourselves of how this works, and I've got an example at the end of a specific type of exponential relationship called HalfLife, which is a pretty important one for medicine and radiation therapies and radioactive materials and stuff like that. So first example I have here is an example of an appreciation scenario where a student bought a comic book 3 years ago, and they bought it for $2.50. It appreciated in value by 2% each year, which means it gained in value. Something happened with this comic book and it was more valuable as time went by. This can happen with different types of collectibles and all kinds of things. Your house, for instance, can appreciate in value. What is the equation that models this scenario? So before the holidays, we had been looking at these, and I had told you that the equation is usually written as, let me choose a pen here, y is equal to a times b, which I like to put in brackets, to the power of x over d. So the a is your starting value, the b is your growth or decay rate depending on what's happening, and the b is always compared to 100% to start, and then we have to convert it into a decimal. The d controls whether or not this quantity, which is the value of the comic book, is changing with let's say this one is changing with a time value. So this one is changing each year, which means every 1 year. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 years. But sometimes, as we'll see later on, this quantity could actually change. Let's say it had said every 5 years. Well, if you have every 5 years, this d value would be 5, which would control that. In this case, d was going to be equal to 1. So the b is going to be associated with the 2%. And I'll get to that in a second, but before I do that, I just wanted to talk about the fact that in math, when we're dealing with word problems, we often don't want to write equations using just x and y. We usually like to write these equations using what we call mnemonic variables. Mnemonic variables are just variables that represent what we're talking about. So here, if we're talking about the value of the comic book, we could use v to represent value. So if I write value is equal to, now the initial value, oftentimes in math textbooks what they'll use is this kind of symbol here. The 0 stands for 0 time. So the starting value is at 0 time. So 0 years in this case. So V0, it's a subscript. I've heard it called V naught, as in the knot of a tree. But V0 is the way I usually say it. This is your starting value. Your B is still there. And instead of X, because it's years is a time value, we're going to use T over D instead. And now we can talk about what are all these quantities. So V0, like I said, is your start value. So I'm just going to highlight that in red. And we know that our start value in the word problem is $2.50. So that's what's going to go into that position. Now the B value is how much, or by how much is the value of the comic book increasing? Well, that's related to 2%, but we don't, and this is one of the hardest things about exponentials, is a lot of students just want to shove that 2% into the equation, and unfortunately that's not how these work. It's always, your b value is always based on 100%. So if I'm increasing by 2%, that means that I have 100% plus 2% which is a 102% increase. And you can't use percentages in an equation. You have to convert them into a decimal, and we do that by dividing by 100. And when you divide by 100, you just move the decimal place to the left, so this becomes 1.02. So that's our B value, is 102% or 1.02. And as I mentioned earlier, the D value controls if you're increasing every year or every 3 years or every 5 years or whatever the time value might be. So in this case, our D value here, and I'm going to use a triangle to highlight the D, is each year, which is just 1, so D is equal to 1. So I'm going to put all of those values into the equation in part B here, where it's asking us how much is the comic book worth today, but I just wanted to show you where all those word value or all those numbers come from. So let's solve that first question then. So how much is the comic book worth today? Well, if we bought it 3 years ago, that means 3 years have gone by. So we're just going to put all of our numbers in. So I'm going to try to use this colors here. So we've got $2.50 times our B value, which is 1.02, times, or sorry, to the power of, and this is what makes this an exponential. We had learned this before the March break. An exponential is any equation where the variable, in this case t or x, is in the power. So our time value is 3. So our power is 3 over d, but d is just 1. So I'm not going to write divided by 1 because 3 divided by 1 is just 3. And typing this into a calculator will give you your final answer. I just need to call up a calculator here. I'll do this off screen. You can try it on your own calculators and make sure you get the same answer as me. So 250 times 1.02. And please make sure your calculators are in scientific mode, because they need to be able to follow BEDMAS to do all this in one step, which you should be able to do. And I'm getting a value here of $6.63 as the value of the comic book. That's rounded off, so I'll just put a dot here to show that it's an approximate value. So if I then ask how much will it be worth 10 years from today, well, if today was 3 years past the time we bought it, and these are the tricky things about word problems. You've got to really make sure when you read the word problem, especially if it's separated like in parts like this, to understand, to go back and look at the original problem, make sure you're dealing with the right amount of years. So our time here would be 10 plus 3, or 13 years, because it was 3 years ago that we bought the comic book, plus 10, which gives us 13. So without using color to speed things up, we still got the same 250, we still got the same 1.02, and we still got the same, well, sorry, we got a different exponent this time, which is 13 instead. And if we type all that into our calculator, which I'm going to do right now, so I just realized that I actually made a mistake, because I was getting a bigger answer for the first part B question than I was for the part C question, which didn't make any sense. So I realized that I double typed the 2.5 in the original part B section here. So let me just erase all that. Sorry about that. If somebody was following along their calculator, he probably noticed. So the answer for this one should have been $2.65, and the answer for this one is $3.23. So if you're wondering, it doesn't seem like a very big increase in the amount of money from 3 years, $2.65 to 13 years, $3.23. However, if you look at the graph of this relationship, which I did in Desmos here, so I wrote the equation v is equal to 2.50 times 1.02 to the power of x. You'll notice that from 0 years to 13 years, the change is very gradual. And that's because 1.02 growth rate is not very big. A 2% growth rate per year is not very big. If I zoom out of this window, you will see that it is exponential, but at the very, very beginning of the graph, it's very gradual. So 13 years is not going to be enough to show that much of a change from 0. But it does do the trick. And you'll notice that if you wanted to wait a while for your comic book to be worth a little bit more money, you might, in this case, be waiting a few hundred years. So that's that question. Let's keep going. So here we have another example. This is more of a biological example. So a lot of people might not know what a petri dish is. In biology, when they check to see if something has you can check this for patients when you get a swab for strep throat, for instance. They'll put your swab on in a petri dish. Now, petri dishes have what's called agar, so it's a solution in here, which I believe, I'm not a biologist, but I believe it is a derivative of algae from the ocean. But you can look that up. I'm not a biologist. Anyway, when they swab a petri dish with a cotton swab that they took from, and now it could be from a throat, but it could also be a general experiment that's done in high school is you go around the high school and you swab like doorknobs and your cell phone, and then you put it over top of the agar and then come back a few days later and see if there's any change. And these little spots here are sites where the bacteria has started to eat the agar and have grown. And you can check to see, and there's other tests to see what kind of bacteria it might be, but it'll allow you to actually see the populations of bacteria. Bacteria are microscopic, obviously, but as they start to grow, you'll actually see these spots on the agar. So you can go look at that online if you're interested in more information. So a population of bacteria, or any kind of population, I'm going to use bacteria in this case, increases in number by 4% every 5 hours. So this is a difference between the original question that we did on the previous slide and this one. In the previous slide, it was every year. Now we're looking at every 5 hours. Now the time unit, I mean, it does matter in the context of the question, but it doesn't matter in the context of the equation. Every 5 somethings. So this is not changing every hour. It's changing every 5 hours. And this is why we need that d value in our original slide. So as you see, the d was equal to 1 because it was each year, but d is going to be equal to 5 in this case. So I'm going to put the red triangle around that right away, just so that we see it. We still have a b value. Our b value is, I'm just going to make sure I'm using the same convention here, so it's a green circle. So our b value is 4%. And we used a red square or rectangle to represent our starting amount. Now in this case, our starting amount is the number of sites we have. Oops, sorry about that. So, okay, yeah, I just remember this is supposed to be a purple triangle, not a red triangle. So here's our red rectangle. So our original sites, our starting amount of sites which are these dots in the Petri dish. I know the picture doesn't match the question. There's a lot more spots than 3 here, but you get the idea. So if I want to write the equation, because this is a population scenario, I'm going to use P instead of V, and it's going to be P0 times B to the power of, and we're talking about time again, so T over D. And this time we're going to need that D. So, purple triangle. This is related to growth, and this is related to our starting amount. So reading a word problem, as long as you kind of understand the setup of what they look like, and you know what the formula looks like and where everything goes, eventually you get to really be comfortable because they're always written very, very similar way. And if they're not, you can learn, the percentage is always connected to the B, and they'll talk about something about the start value, and then potentially how much the time is affected by every value like this. So it's really not that difficult once you get used to it. So P is equal to 3 times our B value. Now our B value, we have to calculate it again. It's 100 plus 4%, which is 104. Oops, sorry about that. So it's 104%, which gives 1.04 as our growth rate. So not a big growth rate, 4% every 5 hours. So our 5 is going to go here because that's our time value, and our D is going to go here. Oh, wait a second. Sorry about that. It's not 5. I thought it was 5 hours as in how much time has elapsed. So our T is just T in this case, and our D is 5. Sorry about that. Okay, so that is our formula. Now I'm going to need that on the next slide, so I'm just going to try to copy that so I can move it over to the next slide. So I should be able to lock this in place. Okay, let's see if I can select this. And the next slide says how many sites will there be in 72 hours. So I'm going to paste my formula. So there's our formula. So 72 is going to be the T. I had made the mistake on the previous slide there. I thought this was 5, but 72 hours, and 5 is in hours, so we're good. But as a little bit of foreshadowing, this one's in days, not in hours, so we're going to have to do something special about that. But 72 hours divided by 5, so we're going to put 3 to the power of, times 1.04 to the power of 72 divided by 5. Now, because we have a fraction in our power, I always try to suggest to my students to put brackets around that. You can do all of this in one step on your calculator, 3 times 1.04, putting brackets around the 1.04 to the power of bracket 72 divided by 5. So if you do all that in one step with the brackets, you should get the correct answer. So I'm going to do that off screen here. You can do it on your own calculator. So that's giving me an answer of 5.3 sites approximately. Now, sites you would think is a number that can't be written as a decimal, so some people might think, well, we should be rounding this to 5 because 0.3 means we don't have a full site. However, if you remember the picture of the Petri dish, I'll actually just go back and show you. You can have smaller sites that are starting off of a main site. So that would be the 0.3 in this case. So in this case, I am going to leave it as not just integer whole numbers, but decimal values. Now the next question says, how many sites will there be in 10 days? Well, we have to convert 10 days into hours because our 5 is in hours, and you're not supposed to have two different units in the same question. So to convert that, we know that one day has 24 hours. So 10 days times 24 hours per day is going to give us 240 hours. So that our units must be the same. So now I can use the same formula again, but my t is going to be 240 instead of 72. So p is equal to 3 times 1.04 to the power of bracket 240 divided by 5. And once again, using our calculator, I'm just going to do this off screen. So 3 times 1.04 to the power of bracket 240 divided by 5. Sorry, 240 divided by 5. I just typed in 250 by accident there. And that gives 19.7 sites. And because these are word problems, we should really have a sentence. I forgot to mention that. I'm not going to write the sentences here just for the sake of saving time. But you would say something like, therefore there would be 19.7 sites in 10 days. So those are the types of questions. The hardest part of these questions is coming up with the formula, but I'm hoping that you're seeing that it's not that difficult to come up with a formula if you can identify your three main components. We're now going to look at the last kind of question, which is a half-life question. So half-life is a term you're going to hear a little bit of in a lot of exponential scenarios because it comes into play when we're dealing with anything that deals with radioactive particles, and it also comes into play in medicine because a lot of times the amount of a drug that's left in somebody's system is measured with half-life as well. So for instance, if you go online, you can actually look up the half-life of coffee. And the half-life of coffee, it says here, the half-life of caffeine, time taken for the body to eliminate 1/2 of the caffeine varies widely between people depending on factors such as age, body weight, etc. The half-life is approximately 5 to 6 hours. So if you drink a cup of coffee, it'll take 5 to 6 hours for half of that cup to leave. So if you started with 1 cup, you'd still have half a cup's worth of caffeine in your body 5 to 6 hours from now, and then another 5 to 6 hours you'd have a quarter of that, and then another 5 to 6 hours you'd have 1/8. So it takes quite a while before these things will leave your body, and people like athletes have to be careful with that kind of thing because if they have a cold or something, some athletes have been disqualified from even Olympic medals, because it takes such a long time for some of this medicine to leave, and certain medicines can be considered a way of enhancing your athletic abilities, and you're not supposed to do that. So anyway, what is half-life? Half-life is the time it takes for half of the things to leave the system. And if you're talking about radioactive particles, it's the amount of time it takes for half of the atoms to decay. So if you started with 1 kilogram of radioactive substance, after the half-life time, you'd only have 0.5 kilograms of that particular substance left, because half of it would have gone away into the atmosphere due to radioactive decay. So carbon dating works this way. If you want to look up carbon dating, there's a certain amount of radioactive carbon that we breathe in, and it stays in our bones with the regular carbon that we breathe in. And you can, if once you die, you are no longer bringing in any carbon. So all of that carbon is locked. Well, scientists know how much carbon 14 should be in your body, and therefore, if it's not the right amount, they know that it's decayed, and they know the half-life of carbon, so they say they can figure that out. So there's a lot of uses for half-life. Now, the only thing that changes with half-life is they didn't tell you the growth rate, or in this case the decay rate, because this is leaving your body. We know from before the holidays that when you have a decay, your B value is a number that's between 0 and 1. It's a decimal value between 0 and 1, so like 0.5, 0.75, and that means that you're decaying instead of growing. Well, half-life has the word half in it, so B is equal to 0.5. And that's one of the biggest and only changes in this question. The other one, before I get to that, I listed a few half-lives here of some radioactive materials, so you can see lithium-8 has a half-life of 0.838 seconds, whereas uranium-235 has a half-life of 703 million years. So there's a pretty big range of half-lives for your different elements here. Now, the other change that I was going to talk about is, instead of using D for half-life, oftentimes textbooks use lambda. It's a Greek letter. It's used for a couple of things in science, but one of the things it's used for is radioactive decay. And there's actually a computer game called Half-Life, and this is the icon that they use on the cover of the game. So some of you might have seen that if you've ever played the game Half-Life. But that's really the only two changes, and I talk about that right here. So if we take a look at 3 grams of krypton. Now, krypton 89, this 89 is a number that is basically a red herring for some students. If you haven't taken chemistry or physics yet, krypton 89 is just an isotope of krypton, which relates to how many neutrons are in the nucleus, and depending on how many neutrons, there are different types of elements on the periodic table. Krypton 89 being, an isotope of krypton. So it just means that it's a little bit more unstable and therefore radioactive. So if you take physics and chemistry, you'll learn about that. But this little dash here just means that it's attached to the type of krypton. This is not a number that's going to appear in our calculations. So our start value is 3 grams. Our B is related to the word half-life, which is 0.5. And if we look back at the chart from the previous slide for krypton, it is 0.838 seconds. So that's actually our D, or lambda, in this case. So 0.838 seconds from the table. And that's our new D value, or our lambda value. Lambda, to draw it, it's like you just do a diagonal kind of curve going. It's like a backwards S, and then you put a leg beside it. So it's not the easiest thing to draw if you've never drawn it before, but you could always just use D if you want. So this is a calculation of a final amount. So oftentimes we will use A for these types of questions. They're all the same equation. It's just using a different mnemonic letter to represent what it is we're calculating. Remember, A0 just means the starting value. This is a subscript. I haven't mentioned it in a while. I'm just going to mention it again. Times B to the power of, and we are talking about time, so T over lambda now. So for half-life, and I'll put this in brackets. So we do have an issue with the 838 seconds, 0.838 seconds being in seconds and the time being in minutes. So we have to convert our time to being in seconds. So 45 minutes and we know that there is 60 seconds per minute. So one way that you can do conversions like this, and a lot of people know that they just multiply the two of them, but there is a way to look at it in the sense that if you multiply this times this, the minutes cancel and you're left with seconds. So we'll talk about that a little later on, but so basically we're just multiplying 45 times 60 here to convert it, which most people know how to do. Again, I'll do this off screen. So 45 times 60 is equal to 2,700. So our final amount will be our starting amount, which is 3 grams. I'm not using units in the equation. I know some teachers like to do that. If I ever need the units, I'll bring them back in later on, but for now, it's just cleaner to not write them down, and that's just a personal preference of mine. Our half-life, as I mentioned before, and you might be saying, sir, it's supposed to be always measured with respect to 100%. Well, it is. It's 100% minus 50%, which is 50%, or 0.5. So it is still based on 100, but half means half of 100, which is 50%. So 0.5 to the power of 2,700 divided by our lambda, which is 0.838. And I'll put that in brackets. And doing this off screen, 3 times 0.5 to the power of bracket 2,700 divided by 0.838, closing the brackets. And this is such a small number that the answer is actually being written in scientific notation on my calculator. So I'm getting 3.7 e, or times 10 to the negative 970, which basically means 969 zeros, 0 point, and then 969 zeros, 37. So there's almost nothing left. In fact, we could almost say that this is so small that there is nothing left. And I didn't know that. I just made these numbers up at the beginning. I didn't know how small the number is going to be, but just to show that this could happen where you get a scientific notation answer. And we've already talked about scientific notation. So that can happen. All right. And I think, even though there is, how much will you have after 2 days? So I'm not going to do that question because if we only have this much after 45 minutes, we're really going to have nothing after 2 days. So I'll have to maybe rejig my numbers that I choose for this question. But just because we got a really, really small answer doesn't mean it's wrong. And there you go. So this is your first lesson for today. I'm hoping to do more. There's no homework right now. If I do get homework, I'll post it to the Google Classroom on other days. But this was just basically a recap and an introduction to the idea of half-life, the idea of this lambda, and just refreshing your memory after the holidays. So actually, one thing you could do for homework is just reread some of your notes from recently and make sure you haven't forgotten everything. That's it for today. We'll see you again on another day.